Okay, welcome to week 9 and lecture 5. So in this week we discussed this stablecoin app, and in this particular lecture we will have a look at kind of the core component, which is this minting policy validator. So first of all, let's just start from the top. So the minting policy has parameters, 3 parameters that are kind of baked in at compile time. And those are, first of all, the hashes of the Oracle validator and the collateral validator. So this is just for basically the minting policy to know the 2 other scripts, so that we sort of are sure that we use the correct one and not some version of it that has been like maliciously modified, let's say. And then we also have as a parameter that is kind of fixed in the beginning, what would be the collateral minimum percentage? So like how much collateral do we need to provide when we mint stablecoins? And then we have 3 redeemers. So remember that the redeemer kind of tells us the different actions that we can do when invoking the validators. So in this case, we can either mint new stablecoins, or we can burn them. So in this case, burn would mean the user herself burns the one that she minted before. Or the other case of burning, which is basically that someone else comes if the position is no longer sufficiently collateralized, and kind of liquidates it and takes the collateral. Okay, and then before we get to the main validator, which is at the end, we have a lot of kind of helper functions, and here they're a bit split into ones that are related to the Oracle, then to the collateral, and then to the minting itself. And we will go a bit through each of them. So the Oracle related ones, so the first one is not so important. This is kind of just a kind of technical thing to get from a pub key hash to get an address that has basically only the pub key and no staking credentials. And the second one, okay, this is kind of intuitive. So we want some way of getting from the script context the Oracle input, so that we can read from it the rate basically. Okay, so what do we do here? Basically, it's just we look at the outputs. We look at the one where the address basically corresponds to the script address of the Oracle validator, which has been hard-coded, as we remember, in the parameters. And we kind of ensure that we have exactly one of them, and this one then we return. And the next one is just to, once we have this this Oracle input, to extract the rate from it. And that we do, okay, first we apply what we just discussed. We get the input, and then from that we use this function that we saw in the previous lecture that is for parsing the Oracle datum and return basically the integer that's just written in there. Okay, next let's go through the collateral related helper functions. And first, okay, this first thing here is just kind of a type definition, let's say, that packages together the datum and the values, so that we can pass both around without much confusion. And then the next functions are maybe a bit similar to what we've just seen for the Oracle. So this function basically given an address and the collateral validator hash just checks that this address basically represents this collateral validator. Yeah, and basically in this case we want the staking credential to be empty, and we want the payment part to correspond to this collateral validator. And then the next function is to kind of get the respective output. So we give it the script context, we give it the parameters which contain the collateral validator hash, and then we basically go through these outputs, and for each output we check if it's coming from the correct address. And then once we have that one, we kind of extract from this output the datum. We also parse it to ensure, so this would crash if it has the wrong format. And then once we did that, we can return it also together with the value, which we will want to use later. Okay, and we ensure that this will be exactly one output, and then we return that one. And yes, here we see we return this kind of collateral output type that doesn't just give us the datum, but also the value, which we will need in the other parts. And here are just two simple functions that kind of extract from this collateral output the datum, just by accessing it, and also take from the collateral output the amount of loveless as an integer, just by looking up the empty string policy ID and empty string token name. Then the next one is kind of similar to this one, but just input instead of output. So we again go through, in this case, the inputs, and we look that the address matches this kind of collateral validator address, and that there's exactly one of them again. And again, similar to getting the datum from the output, we here have a way of getting the datum from the input, and as well for the amount. Okay, then let's get to the minting related helper functions. So first of all, is simple function minted amount that just extracts from the context how many stable coins are minted, and this we can simply do because we know the policy ID and the token name of the stablecoin. Namely, the policy ID is just the one of this minting script itself, and the token name, we have hard-coded them in this comment file that we looked at before. Okay, and here using this get, we just kind of access the dictionary to extract the key, which is the amount of tokens of this policy ID and token name. Then the next one is a very simple check that just checks that this integer is positive or negative, and we will use them in the kind of minting and burning cases respectively. Then this max mint function is kind of an important one. So this is kind of the core math, let's say, of the policy, because it checks or it computes the maximum amount of stablecoins we could mint given a certain collateral amount that has been provided, and given the minting parameters, which contain this collateral minimum percentage. Okay, so in the end we have this formula that you can study yourself if you want to better understand it, but I just want to point out that intuitively the more collateral we provide, the more stable coins we will be able to mint. So we have this here in the numerator, and then so the higher this collateral minimum percentage is, the more collateral we need to provide. So this means the fewer stablecoin tokens we can mint. So that's why here we have it in the denominator. And then we also, it makes sense, of course, to multiply by the rate, because this defines the kind of ratio between stablecoins versus ADA. Okay, and in the end we just divide by 1,000,000, because this is kind of to convert loveless into ADA. And the rate is represented in ADA, not in loveless. That's why we need to convert. And the next function basically just applies this maximint and simply does a comparison. So it checks that the minted amount is no larger than what we are allowed to mint based on the collateral that is in the output and the parameters. Then there's a bunch of checks related to the datum. So in the datum, we want to, so this refers to the datum that is in the UTXO that is at the collateral contract. So that's why we get the collateral output datum here. And then what's written therein is the minting policy. Of course, we want to keep this to be the current, so the minting contracts policy. And then we want to have there written the amount of minted tokens, and this we want to ensure that it is actually the minted amount that we get from the output later. And we also want to record there the correct owner. And in this case, yeah, the owner needs to be someone at least who signed the minting transaction. Next function will be used in the burning case. So in this case, we want that all of the tokens are burned. So the negative of the amount in the datum, so the amount that has once been minted, should kind of correspond to the minted amount, which will be minus what we burn, basically. And in this case, yeah, this is just a simple check that the owner is among the among the signatures. And then the next one is the check for the liquidation. So remember, we only want to liquidate basically once the collateral is not high enough anymore. And one can see that this is exactly the case when the amount of stablecoins corresponding to this collateral input is dropping below what is the minted amount, so the amount of stablecoins. So in this case, basically, max min represents how many stablecoins would this collateral be worth, and in this case, it's less than the amount we have here, which means it's no longer sufficiently collateralized. So now that we have discussed all these helper functions, basically the validator itself is not so complicated anymore. So just note that again, there's this hard-coded parameters, so we don't have a datum read in the minting case. Then we have the redeemer as usual and the script context. And yeah, we just go through these different cases of minting, burning, and liquidating, and in each case we kind of run through all these helpers that we have already implemented above. So okay, first we get the minted amount, so this is the amount that is minted in this transaction. Then we basically, in the minting case, want first that the minted amount is positive, otherwise we're not in the minting case. Then we don't want this amount to exceed the maximum mint, so this is to ensure that the correct number is minted basically and not more. Yeah, note that we actually don't check here that the user doesn't mint less, so because it's basically the user's own fault if they don't mint as much as they could get. Then we also ensure that the datum has like the correct values in it. Then in the burning case, we again kind of first fetch the datum, and then we check basically that the amount that is burned is what we would expect according to the datum. And we check that actually that's the owner who burns it, because yeah, in this case only the owner can burn. If someone else wants to burn, we need to be in this liquidate case. Yeah, and of course we want to actually be this to be a burning transaction, so the amount should be negative. And then in the liquidation case, again we get sort of the right input and datum here, and then yeah, again we want to check that what is burned matches the datum as in the burn case here. And then the key difference is that here, if we basically want someone else to be allowed to burn, then this check liquidation needs to pass. And this is what's exactly the function that checks that now the collateral has sort of dropped below the threshold where it's no longer sufficient to collateralize the amount of stablecoins belonging to this this kind of deposit, let's say. And of course, again, it should be a burn, so it should be a negative amount. Okay, so that pretty much sums up the minting script. So again, in this lecture, we don't cover the off-chain code, but I think already the on-chain code here gives you sort of an idea of what would need to happen in the off-chain code to construct such transactions. And if you want to actually see this implemented, we refer to the Plutus Pioneer program, and these parts are shown in the week 9 and in lecture 5 and 6 respectively. And then now that we have covered the Oracle and the minting part, in the next week, in the next lecture, we will look at the validator for the collateral and the small one also for the NFT. But those are basically the remaining components.